Our big idea so far in this chapter, the area under the velocity curve gives distance traveled. Now we know that velocity is the derivative of distance. We can actually use that relationship to find out changes in other kinds of functions too. If I find the area under any rate curve, I'm going to get the total change in the output, the antiderivative function. So here I have the cola production rate at some cola factory. It's measured in thousands of gallons per hour. If I can find the area under this rate curve, I will find the total amount of cola produced in that whatever time period I find. So here, to the nearest round number, approximately how many thousands of gallons of cola are produced if the graph I'm given is the cola production rate. So just notice I haven't given you a number of rectangles to use or a way to do that. My only big idea here is if I could find that area under this curve, that would give me how much cola got produced in time 0 to 24, so in this one day. So it's not that anybody here told me how many rectangles to use, or I don't know a way to get the exact area, so I'm going to have to give an approximation. Just notice I could count rectangles. That's 1 rectangle, 2, 3, 4. That looks like a 5th rectangle, a 6th rectangle. And maybe this little piece plus this little piece makes a 7th rectangle, and that plus that makes an 8th rectangle. So just as an approximation, I'm trying to approximate the area. This is not an LRAM, RRAM, MRAM problem. I had sort of 8 of those rectangles. Each rectangle was 6 hours wide. And each one rectangle that I counted has a height of 100 gallons. 100,000 gallons per hour. 100,000 gallons per hour. So as an approximation, how much cola got produced at this factory on that one day? Hours cancel. I'm going to have 8 times 6, so 4,800,000 gallons. The big idea there, no matter how you get your approximation, it wasn't specified how to get my approximation here. That would never happen on the AP test. They're going to tell you what kind of approximation to use. But just this fact that I cared to find the area under a different kind of curve. That wasn't a velocity curve, so the answer is not distance traveled, but the area under the cola rate production curve gives the amount of cola produced. Similarly here, I have a function r prime of t, which is the rate at which the radius of a hot air balloon is changing. If I could find the area under the r prime curve, I could find the total amount of change in the radius over whatever time interval I find. So this is use an RRAM approximation to find out how much the radius changes over the interval 0 to 12. I modified this problem and I see I left out a key piece. In the AP test, they would tell you exactly how many intervals to use, or they would say something that made it obvious. So the words I should add in here, it should say, use an RRAM approximation with the sub-intervals suggested by the table to find out how much the radius changes. So that tells me I'm going to use these rectangles, a rectangle that covers from 0 to 2, a rectangle that covers from 2 to 5, one that covers from 5 to 7, from 7 to 11, and 11 to 12. So this is our first time making an RRAM approximation, I think, maybe, where the rectangles aren't all the same width. So notice it's going to be my job to figure out. RRAM means I'm going to use the right-hand edge of each interval. So I'm going to make my width in blue. The width of my first rectangle from 0 to 2 is 2. And the height, let's make it, the height, I'm going to use the right-hand height, 4, plus, maybe I'll do these all at the same time. The distance from 2 to 5 is 3. The distance from 5 to 7 is 2. The distance from 7 to 11 is 4. The distance from 11 to 12 is 1. So that's me going through and writing in all the widths of the rectangles I'm going to use. I'm going to go and I'm going to fill in the heights. That first rectangle at the right-hand edge was 4. The second rectangle has a height of 2, 1.2, 0.6, and 0.5. My units are going to be feet per minute. That's a per minute. Every height of the rectangle was an R prime value, which is measured in feet per minute. And those are going to get multiplied by minutes because all the times, the blues, are the width of the interval. Those are all minutes, so feet per minute times minutes. It's going to give final units of feet. I think it's the final answer of 19.3 feet. So even though I don't know maybe what the radius was at time 0, it doesn't even say up there, I know that from time 0 to time 12, the radius increases by a total of 19.3 feet. Final answer. So assume I want to improve my approximation. I'm trying to find areas under curves for whatever reason I might want to, probably because I'm trying to find distance traveled. If I want to make my approximation better, I have kind of two directions I can go. I can try to use more and more and more rectangles, or I can try to pick a shape, or even specifically a rectangle, that fits the curve a little better so I have less error. So one way that we sometimes try to do that is by using trapezoids instead of rectangles. If I don't make my approximation area flat across the top, if I make it linear across the top, I can sometimes have less error. The top of my trapezoid is going to snug up against the curve closer, and I'll have less error. So you'll probably remember from geometry, finding areas of trapezoids, you find the average of the two bases and multiply by the height. One thing to notice, so that's what I have here. The bases in this case are the parallel sides, the two sides that are parallel. You're going to find their average and you're going to multiply by the distance across the other direction. When I use trapezoids to approximate area under a curve, I'm pretty much always going to have them standing up tall, which means I'm going to have two heights. Those are going to be my parallel sides. I'm going to average the two heights. So to average, you add together and divide by 2, right? So these are the average of the two heights times the distance across the other direction, which I'm going to, in this case, call B, or you could call the width. So now we're going to try using a trapezoidal approximation to approximate area under a curve. And I'm back to my old example. I have information about a velocity curve, and I'm going to try to approximate the area under the velocity curve to find distance traveled. So use data from the table to approximate the distance traveled by the car over that interval. Again, I think on the AP test, they would either be more specific and say use the intervals suggested by the table, or they would say use the 1, 2, 3, 4 sub-intervals suggested by the table. Oh, they did say 4. Okay. So I'm going to use the time intervals 0 to 2, which has a width of 2, from 2 to 5, which has a width of 3, from 5 to 7, which has a width of 2, and from 7 to 10, which has a width of 3. So those are going to be my width. And what I'm going to multiply the width of every trapezoid by is the average of the two heights. So in this case, I don't pick either the left or the right. I take the left and right, and I'm going to average them. So 0 plus 9 over 2, 9 plus 36 over 2, 36 plus 61 over 2, and 61 plus 115 over 2. My units, I'm going to have a width of every trapezoid is a difference in time. So time is measured in seconds. And every height is an average of 2 velocities, where velocity is measured in feet per second. So my seconds are going to cancel out. I'm going to have final units of feet. I'll let you simplify that expression.